Alrighty, welcome back to our calculus examination preparation course. Well, in the previous lecture, we have been talking about the differentiation operation. So, in today's lecture, we're going to talk about the inverse operation called integration. And just like what we mentioned before, integration is much more difficult. Okay, so let's start. Alright, so let's continue about the limit properties. We talked about the uniqueness property last time, and this time we're going to talk about the locally bounded property. So what is it? Well, the definition about this theory is, so if there's a limit, right, for the function f(x), so when x approaches to x0, f(x) approaches to a. So it means there's always exists, a positive number n. So when you will choose x in this range, well, from 0 to delta x, which means you're in the neighborhood of x0, right? Neighborhood of x0, and the range is about 0 to delta x. So there's always means the f(x) absolute value is smaller than n, which means, well, the f(x) is also bounded. Okay, let's look at this on the function graph here. Now we have, this function f(x). Okay, so it means if, we have a limit here, like this one is called a, okay? It's called a. Around, at the point x0, so it means if we choose the neighborhood of x0, right, defined by the formula here, Okay, this is like x0 minus delta, this is like x0 plus delta. So in this region, now we have the f(x), well, in this region. So for example, we can say the f(x) equals to maybe 5 here and 7 here, right? So it means if n equals to 8 or anything which is a little bigger than 7, now we can say f(x) absolute value of it is smaller than 8. So it means, yeah, it is correct because on this point it is 5, on this point is 7, and now on this point is even lower than 5. So we can say that the function's value is also within a certain range. So we can say it is locally bounded. Yeah, locally bounded. Okay, so how can we prove this? For the definite integration, your job is to find out the area. Okay, that's the difference. And no matter for which, for the indefinite and for the definite integration, they have a bridge called a Newton-Leibniz formula, which is about when you're doing the definite integration like this. Okay, so you're gonna find the original function capital f(x) first, and then you let the function value big function f(x), value at the b point and also at the a point to do the difference between them. So we're gonna have this. So that is the area or the value for the definite integration. But for the indefinite integration, you don't have to do this step. All you need to do is to find out one of the original function and put a constant here. Because if you do the differentiation, right, the constant c will become 0. So all of these original functions will become f(x). Okay, so that's why. Alrighty, so after we understand the definition about the integration, so we have to talk about the methods about integration, because in a lot of cases, from the differentiation table, it is not that easy for us to find out the original function, capital Fx. Okay, so the first method we're going to talk about is method 1, okay, is called the substitution method. All right. So in a substitution methods, we have different sub-methods to substitute our original variable such as x, to something else. But the first sub-method is called the trigonometry substitution. Okay, let's see its application range. So usually if we see something like this in our integration problems, and this, yeah, it has the square for the x and also for maybe some other constant. Okay, so why not we starting from this? Okay, so we understand that just because we have the square root operation here, so the x range is from the inclusive, actually, is from the minus a to a, right? Well, does it sound something you're familiar? Yes. Remember in the trigonometry functions, for example, sine, right? For example, sine t. Well, its range is from -1 to 1. So if we just multiply a to this range, or to say a to this function, sine t, we're going to realize this. I'm sorry. Should be minus a to a inclusive. Okay, so that is the philosophy here used for the trigonometry substitution. So we used this substituting function to substitute, well, this variable x with the same range. Okay, so that's why we can have, for this guy, we can write down here, can have, this x equals to a times sine t. All right, we can, since we have let x equals to the a sine t, we can actually draw the triangular to help us understand the relations between t, a, and x. Well, since we have a times the sine t equals to x, so from your trigonometry knowledge, it's not hard for you to imagine a must be this, okay, and x must be one of this one, or this one. Okay, so since it is sine, right, so we understand that it must be this one, x. Okay, and the other side will be a squared plus x squared. Okay, and we have the square root of it. So that is relations between those two sides in a triangle, from our substitution definition here. And also we understand that the t has a range. Okay, so t belongs to this. Okay. Okay, so similarly, we can substitute this one, a squared and x squared's summations square root. So we can have x equals to a times the tan t. Okay, so this time we can also have t belongs to this range minus pi over 2 to positive pi over 2. Okay, and because we have, x equals to a times the tan t, so it's very easy for us to understand that, well, this must be x, and this must be a, and this one should be the a squared plus x squared summations square root. Okay, and we understand this one is t, of course, this one is t. Okay, so let's continue. Alright, so finally, if you follow the same routine, you can actually, well, find it out. This one, the x squared minus the a squared as, so we can have x equals to a sec t. So you can have when x is bigger than 0, we can have the t range as 0 to pi over 2, but if x is smaller than 0, we can have t belongs to the pi over 2 to pi. Okay, so you can take this one as a homework for you, so to see if you can find out why we can use the x equals to a times sec t to substitute the x here. And also, similarly, we can also draw the triangle relations between the ax and t. So if this angle is t, so this one will be x, this one will be a, and this one will be x squared minus a squared's square root. Alright, so in most cases, well, our condition is not that simple, it's other than the a squared plus just x squared. It's not that simple. So generally speaking, we're gonna meet the formulas more like in this format. Okay. In this format. Okay, so this time remember from the middle school or high school's algebra, you can change it to, so you can change this guy, convert. Okay, we can convert it to, okay, one of those forms. So okay, and then see, now you can use the, and then you can perform your trigonometry substitution. Okay. Okay, the second category of methods called the inverse substitution. Okay, I would say method 2 is about the inverse substitution. So this one is actually very simple. You just have x equals to 1 over t. So this one is usually used in a condition where the numerator's order is much lower than the denominator's order. Something like this. So for example, in the numerator we have nth order, and in the denominator we have mth order. Okay, and n should be much smaller than m. Okay. Okay, so the next method we're going to talk about is called the complex substitution. Okay, so as you can see that in the integration, right, your formula is very complex. And for certain parts, it is so hard for you to integrate directly. So you can just have that complex part equals to t to simplify the looking of this integration formula. So for example, if you see something like this in your integration. So you can just have it as t. Or what about this one? Does it look complex enough for you? If yes, you can simply say, okay, let this whole thing equals to t. And then we can have a. Okay. Or this one, or even the inverse trigonometry functions, and so on. Alrighty, so we have been talking about those three integration methods. So now it's time for us to look at one example. Okay, so I would say the example 1. We have such integration. Okay, so of course it's an indefinite integration. Okay, so by observing the format of such integration, now we understand that it looks very similar to something we just talked about, the trigonometry substitution, because it follows x squared minus a squared, right? So we can have x equals to the sec t with the magnitude as a. Yeah, so if we change the x minus 9 to x squared minus 3 squared, so we can convert it to such format. And our a will be 3. So this time we can have, okay, so we will let x equals to 3 sec t. Okay, and the t's range is of course from the 0 to pi over 2. Okay, so after this, we have to substitute the dx. Let's see, the dx will have to be changed to dt. So let's find out the derivative between for x to t. So we have, this is the relation between x and t, so it will be 3 sec t prime here. And we understand that from the basic derivative table, so sec t prime will become sec t and tanning t, right? And then we have a constant 3 on the left. And finally, yeah, so we can change the dx to 3 sec t tanning t, okay, times dt. Alright, so we have changed, well, the integration dx to the 3 sec t, okay, tanning t, okay, dt. Okay, so what about the original integration formula? The function expression as this, right? So we have to change it to, okay, we have to substitute x by a sec t. Okay, we have to do the square and then minus 9, and a here is actually 3. Okay, and then we can have the 3 sec t. Okay, so on top we can have the 9 extracted out. So what is left is sec t squared minus 1. Okay. And this part looks very familiar for us because, okay, I will just put brackets here. Yeah, so this one is actually the tan t square. Okay, so this one is the same thing here. So I would say 9 times tan t squared. Okay, so let's do the square root again, and sec t. Okay, so we can get rid of the square root. You know, we hate so much about the square root. So it's 3 tan t. Okay, on the bottom we have the 3 sec t. We can put this rest here, tan t. Okay, dt. Fortunately, we can cancel out the denominator here, and all we have is 3 tan square t. Okay, dt. Okay, unfortunately, we don't have, you know, the functions derivative in our basic derivative table as the, you know, the tan t square. However, if we change the tan t to something we're familiar with, yes, to this, to the sec t squared minus 1. This is what we had before, you know, for on this part, right? On this part, we use this formula to change the sec t squared minus 1 to the tan t squared. But now we can change it back. Tan t squared equals to sec t squared minus 1. Okay? Okay, now we can do the dt. Okay, so you can refer to your basic derivative table and find out that which function's derivative will become sec t squared. Okay, you found it? Yes, it is actually the tan t. Yeah, tan t's derivative will be the square of the sec t. So the sec t square's integration will be the tan t. Okay, so and of course the you know, for the minus 1's integration it will come t. So I put 3 here. Okay, so that's the one of the original function for our, you know, derivative function here. One of them. Okay. You can write it to this form too. So if we want to find out all the possible original function, we just have to add a constant c here, and c could be everything. Okay, so that's the original function with the variable st. So if you want a variable as x, you just have to put a x in. So we understand that, you know, previously we have x equals to 3 sec t. So this time you just have to do the you know, the opposite direction, inverse operation to have, you know, t expressed by x. Well, to realize this, why don't we draw you know, the triangle to help us to find out the relations between the xt and you know, the a. So according to the definition of sec, of course, so sec means if this is the t, right? So this must be 3, this must be x, so this one will be the x squared minus 9's square root. And of course, obviously, you can have tan t as, well, the x squared minus 9 square root divided by 3. Okay? And also t. And t, of course, will become the arc sec, okay, x over 3. Okay, so let's put it back. So this one will become 3 times the x squared minus 9 square root over 3 minus 3 arctangent x over 3 and then plus c. Okay, so this one will be cancelled out. Alrighty, hopefully you have got the idea about the trigonometry substitution. And that's why we call it, trigonometry's knowledge as the prerequisite course for the calculus, now to the power of the trigonometry functions. Trigonometry is actually very flexible and also very complex because there are so many formulas and each of them has very deep connections with each other. So since we understand that we can use it as a very powerful tool for us to find out the integration in an efficient way. So do you want to try another one similarly? Okay, if you want, we have another example here. Example 2. Using the same trigonometry function substitution method for integration. So let's try it. So we have an integration like this. I think this is actually a simplified version because we don't have sec, right? Yes, and we don't have the denominator. So which substitution do you want to choose? Think about it, pause the video, and give yourself 20 to 30 minutes to see if you can get a good answer. Alrighty, did you pause the video and try it first? Okay. If you got a good answer, you can verify if it's correct. Okay, so if you have trouble, let's go over the whole solution path again. So when we look at this, this is out of the 3 forms in which we can consider the trigonometry substitution. So this one, you can double check, what the 3 forms. So this one, I think we need to choose, the A to let the x equals to A sine t, right? And t, of course, will be within the minus pi over 2 to the positive pi over 2. Yeah, that's the range. So here, because we just have A here, so this is a very standard form. We don't have to do any conversion. So this time, let's find out what the dx will become in the language of dt. So let's do the dx over dt to find out the derivative first. Okay, so let's do the A sine t. Okay, so we have A cosine t. Okay, dt. All right, so okay, so let's put this guy in. So we have this A cosine t dt, and for here we have A squared minus A squared sine t squared. Okay, so let's extract it. So we have we can extract A out first because A is nothing but just a constant. Okay, I will not do anything here, so I will just use this to state. Okay, the remaining will be the same. Okay, so we have this E minus sine squared t equals to cosine t squared, right? And further, we can just do the sine t. I'm sorry, we can put a cosine t out. So we already got rid of the most thing I'm sorry, the very thing we hate the most, the square root operation. Okay, let's add the other things back here. So A cosine t dt, and further, now we can put this A out. So A squared here. So we have cosine squared t here and dt. And now for this guy, from the basic derivative table, of course, you cannot find out whose, which function's derivative will be exactly cosine squared t. However, if we, lower down order of this cosine function, something magic will happen. Okay, so the cosine squared t will become 1 plus cosine 2t. Okay, so if you forgot about this trigonometry function, please review cosine, 2t actually equals to, 2 cosine t squared minus 1 over 2. So that's why we can get this in a versal way. Okay. So here, let's put the 2 out. It's going to have the 1's integration will give us t, and a cosine 2-this integration will give us sine 2t over 2, right? Okay, so this time let's put the 1/2 of the a squared back. So we're gonna have okay. So that's one of the original functions. So if we want to generalize it, we just have to put a constant c at the very end. All right, so that's the solution in the form of t. So if you still want to have the form of x, you just put a the relations between x and t back into the final result. But first of all, let's draw the triangle, the relation triangle. So if this square is t, so from our definition, right? So we can say that, well, this is x, this is a. Okay, so this one will be, all right, so in this way, we can deduct that t actually equals to the arc sine x over a, right? And also for the sine t, we have, the x over a, and for the cosine t, we have the a squared minus x squared square root over a. Okay, so how can we take advantage of the sine t and cosine t, since we only have the sine 2t here? Don't worry, we just have to change this guy to 2 times of sine t cosine t. Well, that's the one of the trigonometry formula. Okay, so let's put everything back in. So we have this arc sine x over a. Okay, so we have this, and we have 2. Sine t equals to this, and cosine t equals to, okay, and plus c. Okay, so let's simplify a little bit. It will be not much simplification we can perform here, but gonna try our best. Maybe just cancel out the this one and this one. So it's gonna be okay, and also yeah, a square will be gone. I'm gonna have this left. C. All right, so that's all. If you haven't really mastered the trigonometry substitution, congratulations. I think you have already got a very powerful tool to maybe resolve half of the complex integrations. Okay, so if you're ready, welcome to continue to our second part of the integration methods.